Okay, I will explain today a fundamental concept in basically anything that you can find. And by anything I mean literally anything, since mathematics can be found basically anywhere at any time. So right now the concept that I'm gonna explain, it's called the natural logarithm. And the reason why I'm gonna explain it is because it is crucial to understand exponential growth and decay. However, right now I'm just gonna focus on the nature of the natural logarithm, so we better understand its nature and its methods to later understand how exponential growth and decay can be foreseen. So right now, let's start with defining what the natural logarithm is. For us to solve these functions with unknown exponentials, we use the natural logarithm. Well, what the natural logarithm is the power of e needed to give x. Now, let me break this down. Now, what we're seeing here is that x equals e to the power of a number. And the natural logarithm of x equals that number that we're looking for, which in this case is the t, the time that we're looking for. Now, the reason why, let me just give a background reasoning of why we use e. E equals roughly to 2.718. Now, this has a lot of history behind it, but basically what e means is the limit basically what it means is the limit as n approaches infinity of 1 plus 1 over n by n, which if you break it down you will see that this basically means a growing number of 2.718 with the infinite decimal numbers behind them, which basically signifies a small growth rate, which can be graphed as, that's the graph of LLN. You see how it's growing, but at a certain point it will grow slowly as the number increases, which in this case will be x. As it increases, it will grow more and more slowly. It will never surpass 2.7, never, but it will grow slowly still. And although we can grow by digits, sometimes these digits can mean billions of dollars. This is why it is important. There is two important properties of logarithms that I want you to really keep in mind, because those are the ones that we will naturally use whenever we encounter a situation where we either face a natural logarithm problem or we want to create one to foresee exponential growth or decay. The two rules that I'm going to explain here, the two properties of natural logarithms are the natural logarithm of f of x equals x, and the natural logarithm of any given number. Perhaps it doesn't has to necessarily be a function, it can be a constant, it can be anything. But what I'm trying to illustrate here is that the natural logarithm of something to the power of another thing is the power of that thing multiplied by the natural logarithm of the first thing. Let me just explain it in an example better. Imagine we have this function, 3 to the power of t equals 10. Now, of course, we want to know what t is, and if you are good at math, you already know what t is. But in this case, we will get the natural logarithm on both sides. Why? Because we want to know what the unknown exponential is, which is what our friends natural logarithms do and help us get. Like I said, the natural logarithm of something to the power of another thing is that thing multiplied by the something. Therefore, now if we divide, because this is still a number, this is a constant, so we can divide that. This is not a function, this is a constant. But we will need to do it on both sides. Therefore, t equals, which, my mistake, natural logarithm of 10 over the natural logarithm of 3 is equals to 2.096. Now we know that 3 to the power of 2.096 equals 10. Now you see how natural logarithm can help us. This example is simple, but imagine if you have a complex formula trying to figure out something more complex and you don't know the exponent. This is where natural logarithms come into place. I will explain with that example in a second. Now, before I give an example though, I want to explain that we can find exponential. Now, before giving an example though, I want to say that we can find exponential functions in nature by two ways. Now, what this function represents is a continuous growth rate, where the growth happens smoothly and uninterrupted, growing by infinite small parts and infinite small intervals of time. So it's very precise. This type of exponential growth function is very precise because it's just continuous. It grows by small numbers and small intervals of time. It grows smoothly and it grows uninterrupted, basically. On the second hand, we have growth rate, regular growth rate, which is basically the rate that you expect to attain on a given interval of time, on a given period of time, or a given parts. Basically, this is a more fixed, discrete growth rate. Like, for example, the growth rate within a year or within a certain months, which is not that less precise, but not as precise as the continuous one. And like I said, the reason why this is important is because those small digits might mean billions of dollars, or perhaps those small digits might mean the best approach on executive level company, or the best approach to take down another competitor, or the best approach to find the solution to a disease or something. What I'm saying here is that those digits matter, whatever your intent is. Now we can interchange between those two writing forms. Let's do an example. Let's say we have the function of the revenue of a company, the continuous function of a revenue of a company with the growth rate of 5% over time. Now we want to find the revenue of a company, not continuously, but on a given period of time. So we want to transcribe this formula in the form of P equals to a quantity of E to the power of K multiplied by to the power of T. We want to transcribe it to P equals a quantity by A to the power of T, which is a growth rate within an interval of time. So how can we do this? Well, if you see here, we have to take it into account that E to the power of 0.05, it's a constant, which it's A. But what's E to the power of 0.05? That's 1.0513. Now we have turned this formula into this formula. What's the difference? Well, the growth rate of 5% is similar to 5.13%. Like, you know how I said earlier that it's not that accurate? Well, it's slightly not that accurate, but this is the growth rate within a period of time. Of course, you will use natural logarithms to figure out what time is, what time you want it to be within that frame. But we know that the growth rate is similar between these two numbers, either 5 and 5.13. This is used to show that we can use both writing forms to find what we want, but of course continuous function is more accurate. And let me explain why with an example. Now let's do an interesting example, a geopolitical example. Well, a geographical example, let's say. Let's say that we want to figure out the population of Nicaragua and how it has grown between 2004 and 2025, right? So let's say the population of Nicaragua in millions was 4.5, right? And the growth rate is given as 4.3%. Okay, so each year it was stated that it grew 4.3%. So let's create a function to estimate how the population grew in these 21 years. We will first get the easy one, the growth rate, which is in the form of a quantity by a constant multiply of t. So here we get the quantity is 4.5 million, but I'm just gonna use 4.5, A and T. So now how do we get A, you might ask? A can be gotten with, if we have the growth rate. So the growth rate A is equals to 1 plus R, which is the growth rate, 4.3%, which is equals to 1.043. Therefore, A equals 1.043. Therefore, our function of the population of Nicaragua as the growth rate within a given time is 4.5 multiplied by 1.043 to the power of t. Right? Now, we want to get the function in a continuous rate, right? In a continuous growth rate. Therefore, we will use the continuous growth rate formula, which in this case, like I said, well, I haven't said it, but K equals the growth rate, which in this case is 4.3. Therefore, the quantity 4.5 million, sorry, let me delete the million, e to the power of the growth rate 0.043. Why 0.043? Because 43% equals 0.4043 power t. Now, this is a continuous function, and this is a growth function. Continuous growth rate within a given period of time. Now, we said that it was between 2004 and 2025, right? Which is 21 years. Therefore, let's plug 21 years in t. And let's do the same with the continuous one. And we get 10.41 million and 10.61 million. Now, remember that this might be more accurate in this case because we are given in an interval of time. However, this function will be used if we want to determine the growth rate overall. But now that I'm saying that, I believe the not continuous function is more accurate, as it represents a small given intervals of time and small changes. So the continuous function will always be accurate. Therefore, in 21 years, the population of Nicaragua was 10.61 million. Increased by 10.61. Thank you.